up. We'll go from current slide. We'll see if this current slide is the same as oh, that was the previous one. Okay. Yeah. Okay. So we're done with that one. And I think this slide is not one that we're going to be doing unless it comes up much later. Okay. No, that was still part of the previous problem. We finished that one. And we finished that one. Ah, this is the one we're on now. All right, before we get started on today, though, let me say this. I hate that it's happening, but it is. As you know, on Mondays and Wednesdays, I basically have no office hours, okay? My first class starts at 8, and then there's a 20-minute break between that one and this one, 20-minute break, this one to the next one, and at most a 10-minute break between that and the last one, and next to the last one, and then there's almost no break between the two physics classes, and then 9 o'clock when I leave, or when I finish teaching, and then I'm usually gone by 9:15 or so. So I just don't have any more. I don't even have 20 minutes in between the classes by the time I shut down one thing and get started on another. So basically no office hours on Mondays and Wednesdays. So Tuesdays and Thursdays, my only office hours, 10 to 12 and 3:30 to 5:15. I've now been assigned to a screening committee for biology instructors, which means yesterday from 3:30 until into the evening, 6:30 I think I was, screening applications. And they're doing a new thing this year and doing it online, and it wasn't working. So I spent most of my time, they were trying to call people, figure out why the system wasn't working, and finally they got it working, so I got 3 screened in that, whatever time that I had there. So that means the rest of my time I'm going to be screening things. But now, since it is online, I don't have to go to Birmingham campus. I did yesterday, though they didn't tell me it was online. I could have done it here and saved myself, but then it wouldn't have worked anyway. But anyway, so tomorrow the odds are all of my office hours are probably going to be spent marking Gunter here. No, I'm sorry, that was Peyton. So probably all my office hours are going to be spent screening applications, which means that some of y'all have turned in some things. I can't tell you right now when they're going to get graded, okay? If I can finish all those screenings tomorrow in the little time in the morning, little time in the afternoon, then when I go home tomorrow evening, I'll grade papers. And then if I haven't finished, I'm going to try to squeeze in some time to do it on Friday too, and maybe Sunday. Usually Saturdays are pretty much occupied, unless we get rain. So I'm praying for rain. So I may not have as much to do if it's raining. So anyway, if you start wondering why the grades aren't showing up, that's why. In fact, as you may have noticed already, the only time grades show up are on weekends anyway, because with those few office hours, very seldom do I have time to get the papers graded and put in Blackboard and attendance and everything. So I catch up everything on the weekend. This weekend is going to be worse because I've got those to do too. So I'm hoping I can get them all done tomorrow. If the system, and by the way, the system crashed once or twice while I was doing it online, so that if it does that tomorrow, I'm not going to finish. But if it doesn't, I might be able to finish. So don't expect to see grades for a while yet, okay? But then they're going to schedule interviews, and if they schedule any on Monday, Wednesday, I'm shocked. I mean, completely shocked, because I've got 4 classes. So I'm hoping they'll do Tuesday, Thursdays, but then those two classes. I mean, I don't want to be on the committee, and I emailed the dean, who's the chair, and said, look, these are my Mondays and Wednesdays. She said, well, maybe you can screen on Tuesday. Oh, yeah. Well, when are we going to interview? But I don't know. We'll work that out, maybe. I don't have great hope in that, but we will. Okay. Any questions on anything before we get started? 4 people here out of, 8 or 9 that we have in the class now, so hopefully others will show. All right. Now, last time we started with partial fractions, and the examples we had were relatively simple, straightforward issues. But every now and then, when you factor a polynomial in your denominator, what you're doing now, basically this is how to integrate rational functions. Okay, rational functions is a ratio of polynomial in the numerator to polynomial in the denominator. I was cramming down half my salad those few minutes I had between things, and I got so much salad stuck between a tooth I can hardly talk. It's irritating, but not your problem. I think I got it. Okay. So what you do, first step is factor that denominator. Leave the numerator alone. It's not hurting anything. Well, okay. Time out. First thing you do is look to see if maybe the numerator is the derivative of the denominator or something close that you can do a substitution. If you can do that, go that route. Okay. If not, then next thing to check to see if that rational function is a proper rational function. In other words, the degree of the numerator needs to be less than the degree of the denominator. If it's not, the first thing you do is divide, long division, whatever it takes, and then integrate the quotient, and then your remainder, it will be a rational function that is, you can do. Okay? But when you finally get it to a proper rational function, then factor that denominator. Now, that's not necessarily always factoring in the sense you did back in algebra, okay, where we used only whole numbers. We're going to factor anything we can, irrational numbers or whatever. Now, we don't go into complex, but we do irrationals. And we'll get to that part later, okay? But when you factor that denominator, you know that occasionally you'll have a factor that is repeated to a certain power. This, what we're going to do now, is that example. So it's a little bit more involved than what we had before. So here is your integral. Whoops. Here's your integral. The integral of 3x minus 9 divided by x minus 1, they've already factored it for you. Thank you very much. Times x plus 2 squared dx. Okay. Houston, we may have a problem here. I can handle the x minus 1. Okay? That's going to be fine. Okay? So what you do is take this integrand, the 3x minus 9 over x minus 1 times x plus 2 squared. Okay? And we rewrite this as sum a over x minus 1, just like we did before. Now you can think of this as a x plus 2 times x plus 2, right? So the next one would be, logically, b over x plus 2. But if you did then another one, c over x plus 2, b plus c is just, still over x plus 2. So that's not going to work, okay? So what we do, here's the trick, c over x plus 2 squared. Now, I guess there's a way to prove that's the way to do it, but it's long, involved, complicated, messy, and not worth our time to do it. Take my word for it, that's what we do. You have one constant over the term to the first power, and then another constant over the second. If that was to the 15th power, then you would do a b over this, a c over this, a d over x plus 2 cubed, the 4th, 5th, 6th, up until you get to 15. So you'd have to have a constant for every power, but you have to have every power represented. Okay? So that's what you do. Where do we go from there? Say that again?
We just solve for A, B, and C.
Okay, you're jumping right to the thing. How do you solve for A, B, and C?
We need to plug in values that make the other
Okay. Actually, one little thing that makes it much easier to do first. This is in fractional form. Oh, yeah. Multiply both sides by your big denominator. X minus 1 times x plus 2 squared. So multiply this. Now, because I don't have much room, I'm going to leave off the x minus 1 and just wipe it out. And then that will leave this times x plus 2 squared. Okay? The next one, it's got to have an x plus 1. And one of the x plus 2's goes out, but not the other one. So you're going to have 1x plus 2 here. Okay? And then the last one, the x plus 2 squareds are going to go, on this side, everything goes out. Okay? But here, everything goes out except the x plus 1. Right? Now that's sort of ugly. So let's pick up down here. All that's left over here is your 3x minus 1. And supposedly that's equal to a times x plus 2 squared plus b times x plus 1 times x plus 2. That's a minus 1. I can't read my writing there. Okay. I can't read it there, but I'm going to fix it so it's maybe a little more legible. You know, I put pluses in everywhere, didn't I? That should be a plus. Okay. It's x minus 1, x plus 2. Okay. And then plus c times x minus 1. Now, at some point you got to multiply out. I wouldn't do it yet. Okay? What's your next step then?
Other variables go to 0.
Okay.
We need to do x equals 1.
Okay, that's one that we can do. Let x equal 1. Now we're using that top equation there. And what do you get when you put x equal 1? I can't write. Yeah, that's a 9. Okay. 3x minus 9. Oh, that's why I miswrote it twice. Okay. 3x minus 9. Glad you caught that.
You get 3 minus 9 is 6.
Like a negative 6? Okay, I thought that's what you said. Okay. Equal to. Now, this is the time when you are going to have to multiply it out. Okay. Can't get rid of that Well, no, we can't. Yeah, let's just plug in x equal 1. Yeah, that's it. What you get?
The 3 squared is going to be 9.
9a. Got it.
And then the, it's going to be 0.
0, and that one goes to 0 too. So there we have it. So a is negative 2/3. Got it. Not as bad as I thought. Okay, using that top one again, what do we try next? Let a equal negative 2. I mean x equal negative 2. Okay, and what does the left-hand side become? Negative 15, is that what I heard? Okay, let me think. What do you decide? 15, okay. Negative 15 equal. All right. What you get?
0.
Yeah, the first is 0, the next is 0, and negative 3c. Okay? And what does that produce? C is equal to 5. All right. Now, what in the world do we do with their b's? Okay? What's that again?
Can't use either one of those numbers because they both give us 0 for b.
Right.
How do you get rid of a and c without getting rid of b?
Right. So, they say in the book, we cannot determine b, like you were just saying, same way as a and c. So, 2 ways to proceed. Okay? One way is to plug in what we know already, what a is and what c is, and so they just pick some other value for x. Okay? Now,
So it's interesting that we know what a is, we know what c is, so we just pick an x and solve for b.
okay. Yeah, basically that's it. Plug in everything else, but you have to pick another number. Now, for some reason, they chose x equal 2, and for the life of me, I don't see any particular advantage to x equal 2. Maybe there is. I'm just really lazy and like to use 0. And 0 is not going to mess up anything. So why don't we use that one and plug in these values for that. Now that's one way. That's called the substitution method. The next is undetermined coefficients, which ultimately is going to get us where we need to be too. So I'll let you look at both of them and see which way you like best. Which would be your druthers right now? Plug in a 0. So let's try it. So let's let x equal 0 with what we know. Okay? I'm not saying that's any better than 2. I haven't done it, but why use a number when you can use 0? It makes it so easy. What does the left-hand side become? Negative 9. Okay? Equal to, now we already know what a is a negative 2/3 times 4 plus, actually it won't be plus, will it? Yeah, it's going to be a minus. So minus 2b, or not, okay, plus, yeah, minus 5. Okay. All right. It's a little messy, but all doable. Now, I think the first thing I would do is multiply everything by 3. I know it makes it a little bigger numbers, but I just don't care for fractions that much, and maybe you love fractions, but you know, whatever. Multiply everything by 3. So how about even a minus 3? Okay, so that will make this a 27, and make this equal to 8 minus 2b. Wait, I'm sorry, I didn't multiply. Plus, what does it say we're multiplying by? 3. 6b. I forgot to multiply that one by it. Okay, 6b. And plus, goodness gracious, this thing is such a pain in the neck. 15. Right? Alright. So let's subtract 23 from both sides, right? 8 plus 15. That will give you 4 on the left is equal to 6b, right? Which produces b is equal to 2/3, I think. Right? I think that's what they got. Both ways of going. Alright. Now, I think we're ready to roll now, aren't we? Your integral becomes that integral there. I don't have much room to write here. The integral of oh, here's the a. Okay, I lost the a. I'm going to put the minus 2/3 in front of dx over x minus 1. B is a plus 2/3 times the integral of dx over x plus 2 plus 5 times the integral of 1 over dx over x plus 2 squared. Okay. Do you buy that? Okay. Now, I hope you see what we were doing. Once you got your A, B, and C, A, C, and D, plug those in up there without all the scratching around it. But the original thing, A over x minus 1, B over x plus 2, and C over x plus 2 squared. Okay. Now, and they're each separate out the intervals. First two, fairly straightforward. What is it? Got it? Okay. Now that next one might need a little bit of help. Anyone want to hazard a guess or come up with? Second? Okay. Say that again.
Negative 5 over x plus 2.
Okay. Negative 5 over x plus 2. Okay. And then, you, of course, you have a plus c somewhere up there. Okay. Now, let's, did y'all all see how he did that? Okay. I don't know, did you mentally do a substitution or just do it as a unit? Okay, yeah. If that had been, say, an x, x plus 2, x squared, or in other words, x to the minus 2, that would be the, when you take antiderivative, you go to x to minus 1 over minus 1, so that's where the minus came from. And it's x plus 2 squared, so it's just same kind of thing. If you needed to do a substitution, you'll find out it works just the same. Okay? So, that, I think, that is our answer. Let's see if that's their answer. Okay, and by the way, if you'll notice, this line here that we right in the middle of writing, in the text, they use A, B, and C, and that's what I've always used. But in the previous edition, since it had the same similar denominators, they used B1 and B2. Now, never for the life of me figured out why they did that. B and C work just as well, and this line is basically just what that line is, except we're using a B and a C rather than B1 and B2. That's exactly where that came from. So, okay. Let's see what they do next. Okay. This is their technique, which they showed as the second method, I think, yeah. Which they called undetermined coefficients, which certainly is one way you could do it. But we chose to do it the other way, so if you need to see this, go back. That's exactly, or not quite. In your text, they multiplied out the x plus 2 squared, whereas this one they left it in that form. And then they also multiplied the x minus 1 times x plus 2, which doing undetermined coefficients, that's what you got to do. It's a little tedious, but it's all doable. Okay? Then they wound up in this form, which is exactly what we had, minus the a is negative 2/3, b is 2/3, and c is 5, and then put that back in the integral, and okay, that finishes the problem. So let's see what answer they finally wound up with. Negative 2/3 log absolute value x minus 1 plus 2/3 log absolute value x plus 2 minus 5 over x plus 2 plus c. Correct. They got it. Now, and again, as I was saying before, if that rational expression is not proper, which means the degree of the numerator is greater than or equal to the degree of the denominator, divide first. Do your division. Generally, it's going to be long division. Occasionally, you may wind up easy to do synthetic. Most of the time, it's going to be long division. And the next problem is going to lead that way. Okay, we already did those two slides. And they're not showing one like it yet. I think this is jumping to the next. Yeah, this is the next deal. So I'll use this one. Okay. Let's evaluate this integral. X cubed plus 1 over x squared minus 4. Okay, and that's the dx. Now, what you do first? Say again? Yeah, this one you cannot avoid dividing. Now, mentally, I checked it because I knew that denominator was factorable, x plus 2 times x minus 2. And I know that numerator is factorable, not very prettily, but it is. The first factor would be x plus 1. The next factor is going to be a non-reducible quadratic. So I know that neither x plus 2 nor x minus 2 is going to go into x plus 1 or that non-reducible quadratic, so that wouldn't do me any good. So don't bother. But look, see if, because it could be that if they factor properly, you could eliminate some things first and make life a lot easier. This one doesn't, so don't waste your time. Do you remember how to do long division? What goes where? You have a house here. What goes inside the house? What goes outside the house? Second? The top goes inside. So what would you write? X cubed. What did you say? No, not quite. Here's the thing with long division. You've got to account for every term. So you have to put a 0x squared and a 0x before you do your plus 1. Okay? Now it's not absolutely necessary to do on the outside, but I think it really is helpful there too. So I would write it as x squared plus 0x minus 4. Okay? Otherwise, you get things out of line, crossed up, and you just increase your probability of making an error. So minimize that. Fill in, have something representing each term. Now what? Remember, in long division, it's the one operation you go left to right rather than right to left. So you start with the first terms. X squared will go into x cubed how many times? Not 1. X times. Because when you multiply, what do you get? X times x squared is x cubed. X times 0x will be plus 0x squared. X times a minus 4 minus 4x. Now you see why it's helpful to have that 0 in there? Okay. You might could have lived without the first one, but how do you know that ahead of time? So put them all in there, save yourself some grief later. Now, usually with division, what do we do? Subtract. You're going to do that here too, but you've got signed numbers, so I like to go to the rule for signed numbers. When you're subtracting, change signs and add. That just makes it easier. So I'll make this a minus, 0, it doesn't matter at all, make that a plus, now I'm going to add them. These go away. These weren't there in the first place, okay? So what do you have? 4x, and bring down the 1, okay? Now I take a look at that and I say, I know that the x squared won't go into 4x. You've got a remainder here, so I'll write it like this. Plus 4x plus 1 over x squared minus 4. That becomes what you had before. That rational expression becomes this. A polynomial expression plus a rational expression. So what we do here, we write the integral of x dx, I think we can handle that one, plus the integral of 4x plus 1 over x squared minus 4 dx. Okay? And as I said, I think we can handle that first, right? What is it? X squared over 2. Okay. Now the second one, we're back to a rational expression. It is proper, so going to have to do, well, wait. Seeing if a substitution might work. The derivative of the denominator is a 2x. It would be messy. I mean, okay. If you split this into integral 4x over this dx plus 1 over that dx, then you could handle that first one with a substitution, and then you just have the other. Or we can just proceed with here. You're going to get the right answer either way. I'm confident you will. Which way would you rather do?
If you substitute, you make it 2du over u.
The way it is now?
This-
Yeah. Yes. The way it is now, you can't do a substitution. But if you split that as the integral of 4x over x squared minus 4 dx plus 1, the integral of 1 over x squared minus 4 dx, then you can use a substitution on that first one. You can use the substitution when that's your numerator. You'd have to do partial fractions from that if you split it. Or you can just do it once and do it again. Let's do it once, okay? So, what would be your next step with? Let's go over here to the side and do 4x plus 1. What do you want to put it over?
It's the bottom factor.
Yes, so factor the bottom. It becomes,
X plus 2x minus.
got it? Okay, and that's equal to a over x plus 2, b over x minus 2. Got it. Now your next step?
Multiply with the denominator.
Yeah, clear those denominators. I'm going to do it on the left-hand side. There, I did it, okay? Just wipe them out, okay? On the right, so that leaves you a 4x plus 1 is equal to, and when I multiply that denominator that I had on the left-hand side by the first term there, what do you get? A times x minus 2. And when I multiply the second one, I get a plus b over, times x plus 2. Now, I skipped some steps there. Are you okay with it, everybody? I'm just lazy sometimes. I don't have much room to write, so I'm trying to conserve space. You see what I did, everybody? Okay, good. All right, now what? Help me, help me. Let x equal 2. I like it. What does the left-hand side become? 9 is equal to, I'll do the first term, 4b. So what does that imply b is? 9/4. Oh, one of my favorite fractions. Okay. And secondly, we'll let x equal negative 2. So the left-hand side becomes negative what? 7. Yeah, I agree. Right-hand side becomes minus 4a. A. And what does that produce? Say that again. I was thinking it was a 4, was it? Isn't it? Yeah. 4. Oh, okay. I thought you said, okay. Okay. I don't hear well. Sorry. Okay. Another one of my favorite fractions. Okay. So what does this produce? 2 integrals. The first one is, I'm going to pull the 7/4 out, and that will be the integral of dx over, yeah, I'm trying to, there it is, x plus 2, isn't it? Okay, that's what I was looking for. I couldn't find that on the page. And then plus the b is 9/4, times the integral of dx over x minus 2. Okay? So this gives you x squared over 2 plus 7/4 natural log of absolute value x plus 2 plus 9/4 natural log absolute value x minus 2 plus c. Don't forget your indefinite integral requires it to be a plus c. All right, let's see how they did. They put 1/2 x squared, same as x squared over 2, plus they put the 9/4 in front. It doesn't matter, 9/4 log absolute value x minus 2 plus 7/4 log of absolute value x plus 2. Yeah, and then plus c. Got it? Good. All right, any questions on that? When you have one like this, that you have a repeated or multiple factor in your binomial factor in your denominator, then you have to do a separate constant over first that to the first power, then to the second, however many the multiples are, up to that. Okay. Excuse me. Okay. So we're moving on to what if you have a quadratic factor? Okay. Now, this is their answer. I don't recommend that you try to remember that's what it's going to turn out to be. Okay. I think it's just about easier to actually do the work. I'm not a memorizer, so I'm not about to try to memorize that and remember what goes where. It's easier for me just to go on and do the same thing we did, but here is the situation. When you have a quadratic polynomial, ax squared plus bx plus c, okay. Now notice they didn't give you numbers there, but that's your denominator, somewhere in your denominator, and you can't factor that. You can't change it any, not even with irrational numbers, okay, can you change that. Then what you do is, that's called an irreducible quadratic. If you cannot factor it any way, shape, or form, that anything you try is going to come up being a complex number or something else like that, then that is completely irreducible. Okay? And when you have an irreducible quadratic, then you, for every one of those that you have, now they throw the whole kitchen sink at you to begin with. They say, what if you have this irreducible quadratic raised to some power m? They're going to cover everything in one step here. That's your denominator, whatever your numerator is. That's your denominator. Or it's in your denominator. It may have other factors too that are binomials, that you can deal with. But you have that. Then for every one of these you have, then you set that equal to, and this is the place to use the subscripts 1 and 2. Since that's a binomial, your numerator is going to be 1 degree less for every term. Ax plus b, and since you got multiple terms of them, we'll call those a1 x1 plus b1, sorry, over this ax squared plus bx plus c. Now, just if you were hearing that without seeing it, I don't know if any of you are in that circumstance over at home, that you can't see the visual but you hear it. The numerators are capital A's and the denominator are lowercase. They have nothing to do with each other at all. They're just, this is A1, capital A1x plus capital B1, and then the denominator is a little a x squared plus little b squared x plus little c. Okay, so don't think just because they use the same letters there's any connection. There's not. They're completely different entities. But if you had more than one of these, then you'd also have to have a term with some other a2x plus b2 over ax squared plus bx plus c to the second power. That one's to the first, that one's to the second. And just like we did before, you have another set of numerators. And in this case, it's easier to do A1s and B1s, the A2s and B2s. If you just strung out the alphabet and AX plus B over that plus CX plus D over that squared plus DX, but you like I just did there, I ended with a D and started the next one with a D. You couldn't do that, you need an EX. So it's just easier to do the term, the linear term is A sub n, and the constant term is b sub n. You know, it just keeps it a little bit nicer. If you want to use A, B, C, D and use the whole alphabet several times over, you can. It doesn't bother me at all. Okay. So let's do an example of that, not an integral, but just an example. What if you had 4 minus 12x is your numerator in your integrand, and your denominator simplified as much as it could to a plus 1 . I'm having trouble with my eyes today. I don't know what it is. They're dry, but the glare or something is just really coming close to giving me a headache. The second factor is an irreducible x squared plus x plus 4 squared. Okay? They had to do that, didn't they? Okay? Now, I hate when they do things like this. They gave you the answer. Let me give you the process. What do you think you'd put on top? First. Second? A. Why not A? A over what? X plus 1. That's all you need. That just needs to be 1 degree less than the denominator. Okay? Plus. Second? A2. You could do that. You certainly could. Since I already used the A there, I'd be tempted to use a B1 plus C1, B1X plus C1, but that's perfectly fine to do that. Which did the book use? Oh, they didn't. I'm sorry, they went right to the answer. So, yeah, A1 is fine. A1X plus B1 over X squared plus, I think that's an X plus 4 squared. No, I'm sorry, that's to the first power. I was thinking the first term I'd already squared it. Whew, I'm jumping ahead. Okay. Yeah. Plus what? A2x plus B2 over x squared plus x plus want 4. I'm sorry. Couldn't find my thing. And this time, that's squared. Same thing over now, if you don't like all the A's and you're afraid you're going to mess them up, then make the second ones a B1 plus C and this a B1CX, a B1X plus C, a B2X plus C2. You can do that too. You can do it any way you want to. If you don't mind having 3 A's in there, this is perfect. Okay. Now, yeah, let's go ahead and do it. I was going to say, because we know they've already shown us in the book what they are. These are going to work out reasonably well. What would you do next? Yeah. So that's going to wipe out this and that. This here, and that leaves you, what do you multiply by the A? X squared plus X plus 4 squared. And this one will wipe out that, and you'll have a X plus 1, because that was in there, and you'll have an X squared plus X plus 4. That's going to be a pretty big term, okay? This one, both of these will cancel out there, so this thing is just multiplied by X plus 1. Okay? Now, not a trivial thing to do. The closest to coming trivial is that last part. And that's still not very trivial. I mean, it's okay, but it's not really. Yeah, so first thing you've got to do, or I would recommend doing, is squaring this. Now there's a rule for binomials. Trinomials, you just got to brute force through it. Okay? And then when you get to this one, I don't know which is, I don't think there is a best way. You can either multiply these two and come up with another trinomial, and multiply that one, or multiply this one by that one, and get a trinomial, and then multiply that by here, and that might be the easiest way. This one's by far the easiest so far. Okay? But as you notice, you're going to come up with 5 unknowns. So you're going to need 5 equations, or at least it appears that way. But you'll get them. So first thing I got to do is square that binomial. X squared plus X plus 4 times X squared plus X plus 4. Okay? Seems sort of crazy to do it this way, but I think it does work out best. Oh, wait. Sorry. I forgot. Let's at least do your x equal 1. Wouldn't you? I mean, x equal negative 1. So before we go this far, we're going to have to do that after a while anyway. But let's do what we can now. It's the only one we can do, x equal negative 1. So let's get that one done. And what do you have? Second, 16? Yeah, 16 is equal to? Say that again. Okay. Second. Yeah, you may be right. I was doing it quickly and didn't get that, but I see I forgot to square it. So that would be 1 minus 1, yeah, 16. 16a. And guess what? The other twos go to 0. Yay, thank you very much. So this produces a is equal to 1. And sure enough, they have 1 over x squared. I mean x plus 1. Good. Now that helps things a little bit. You don't have anything else you can do, so it's kind of like we did before. We have two choices. Let's write down what we have now. We have 4 minus 12x is equal to x squared plus x plus 4 squared yeah, because a is 1. And here, like I said, you postpone as much as you can, but you can't get rid of everything. And there you're just going to have to start multiplying out. Because this is a big pain in the neck, and they just threw that out there and said, there's what the answer is. And it works, okay? I don't think it's worth taking class time to do all that, because it is a pretty hairy problem. Let's wait and see the ones they gave us, which hopefully won't be quite as bad, okay? No promises, but it wouldn't be, okay? They also said you may need to use trig substitution. That's what this one is. And I guess I was saying I don't memorize it. I look it up in the table. If I need it, I look it up in the table. But that's what they're saying. I thought they were saying this is the solution for it, and I was going to carry you through that. But no, that is the, when you look up in the table, that's what it gives you. Okay? Which, if you do a quick timeout here and think about all your answers you've had so far, they're either as a polynomial, a log, and now we have inverse tangents. Okay? So I think that's going to cover much of what our needs are. And we'll go from there. So let's stop with this one and go on with example 5. I don't think there's anything on here, so I'm going to erase ink if that's okay. But on example 5. Okay, we got 2 of them. Let's do the first one first, 5a. We're integrating 18 over, again I'm having trouble reading, x plus 3 times x squared plus 9. Okay. That did not come out very pretty. So let me do it. Again, my eyes are giving me fits here. X squared plus 9. Okay. And that would have a dx. How would you begin? Let's write that integral. 18 over x plus 3 times x squared plus 9. And by the way, that quadratic, can you factor it? Not in the real number system at all. have to go to imaginary, three eyes. We're not going there. Not going to introduce that. So this is where that's called irreducible quadratic. So we're going to leave that just like that. And what would be your assumption of an answer? A over x plus 3 plus, okay, no, you have to have one left degree. Bx plus c over x squared plus 9. Okay, that's what was implied before and sort of done before, but for any irreducible quadratic, its coefficient is going to be a linear term. And you have to have both a linear part and a constant part. You could call it a1x plus b1 if you wanted to, but since there's no more numbers in it, let's just leave it like that. Okay? What's your next step? By the denominators. That'll wipe this out, leave you on the left-hand side 18. Okay, it'll wipe out this and just leave you an a times x squared plus 9 plus, and this one will wipe out the 1 and give you a bx plus c times x squared plus x plus 3. I'm sorry. I got lost what I was doing there. Yeah. Right? Now. Next step. Okay. X equal negative 3. And that would, left-hand side is still 18. Nothing changes there. Equal to 18a. Second? Plus 0. So this implies that a is equal to 1. All right. Now we come back to one of those situations you can't do anything else with it. So, with that value for a, and just pick another x. Have a favorite? 0. Why not? Okay. So let x equal 0, and we're going to plug it in with the a value there. Left-hand side is still 18 is equal to, 9 plus okay, c times what? 3c, right? 3c, okay. It's not erasing. Okay. Yuck. Okay. Now. Got a little problem, don't we, Houston? By choosing the 0 there, we lost any chance of getting our B. So maybe 0 wasn't the best choice. Or that gives a C and then choose something else to get your B. Okay? So what does this produce? Let's go on and proceed with this. What do you get? 9 is equal to 3C, implying C is equal to 3. Right? Okay. I can't decide whether that was a poor choice or we're going to have to do something else anyway. So this time pick another one. Let x equal 1. Okay. Left hand side is still 18. Is equal to your a was 1. There, I keep getting lost here. X equal 1 and a was 1. So this gives you, what do you say, 10. Okay. Plus, okay, b is still an unknown. X is still an unknown. Goodness, my head is just going. That would just give you, C was 3. So that's b plus 3, right? Yeah. B plus 3 times 4. Okay. Let's see what that produces. Let's subtract the 10, make it 8 is equal to 4b plus 12. Subtract 12, and you get a minus 4 is equal to 4b. So b is equal to negative 1. Now, your integral now becomes dx over x plus 3, that's your a, plus, let's write this one out, 2, b was minus 1, so I'm real tempted to I'll put minus x plus 3 over x squared plus 9, isn't it? Okay, dx. Okay, I think I wrote it right. All right, now. Okay, this time, I don't think there's any way to avoid splitting that integral into two pieces. I don't think there's a trick that's going to help you out. I know you can't factor that one. So I think the best thing is to split that. Well, let's do that first integral. What's it? So we don't have to keep writing it. Log of absolute value x plus 3 plus, only it's going to be a minus now, I think, if I haven't made a dumb error. Goodness gracious. Whew. Minus the integral of x dx over x squared plus 9. Yuck. Okay. All right. And plus 3 times the integral of dx over x squared plus 9. Okay. I know that's getting awfully messy there. I think what I'll do is erase this, get it out of the pictures to get rid of some of the clutter. We've already used it and it's over with. Okay. So we got our log, natural log of absolute value x plus 3 minus. What here? Any ideas? Substituting u for what? Let u equal x squared plus 9. Okay? Then du is equal to 2x dx. Okay? We don't have a 2x dx. We have an x dx, so let's divide by 2. Okay. Yeah, okay, I see. I lost what I was, there it is. Now that integral will be, you'll have a 1/2 out front. Okay. And that will be your du, because you already pulled out the 1/2 over u, and that would be, well, I have to write it, du over u. Okay, we'll come back and do that. Okay, how about the next one? Plus 3. What do we do with that? This is where you look it up in the table, or since we're on the same board, we'll use this. Okay? This integral right here is exactly this one with a equal 9. Okay? So that would be, I don't want to recreate it, so let's just give me the answer. One over 3, right? Okay. Inverse tangent of x over 3. All right. I'm going to have to get rid of some of this too. It's just too crowded. Okay. Okay. And I think we'll do a plus c then. Okay. Now, this becomes log absolute value x plus 3. I can't write. Minus what? 1/2 of u, which is your x squared plus 9. Now, on that one, lose the absolute value bars. We're not letting x go into complex, so x squared is always going to be positive. Adding 9 to a positive number is always going to be positive. I mean, x could be 0, but adding 9 to it keeps it positive. So leave it in that form. And then this one is the 3's cancel out, plus inverse tangent of x over 3 plus c. All right, I sure hope that's the answer they get. My head's going crazy. Now they came up with a is equal to 1/2. How did they do that? I've already erased too much stuff, I'm afraid. Am I on the same problem they're on? Wait. Oh. No, I'm not. Oh, I'm sorry. I'm looking at the wrong page. The problem is almost identical to it. So here's what we got. Here's the answer. Okay. Whew. That was driving me nuts. Okay. Log x plus absolute value x plus 3 minus 1/2 log of x squared plus 9, not absolute value by the way, plus inverse tangent of x over 3 plus c. Same thing. Now we're going to go to the b part. Looks almost the same, doesn't it? What's the difference? X squared minus 9, not x squared plus 9. That one can be reduced. I hate to do this to you, but I've got to go get something for my throat. And in the process, I'm going to rinse my eyes out too, because I think what happened, I just basically tried to eat as much salad as I could without drinking more than a swig of water. So I think I'm just too dry. So let me pause this just for a minute. Okay. Now, there was the A part, messy as it is. Sorry. Let's do the B part. I'm going to erase all this. The B part is just with the minus there. Wish I could erase all but that, but I've got to erase it all. Sorry. Oh, I guess while we're on the screen, there was the A part, how we set it up just like we did. Okay, and they got to the same next step that we did. And they got the B equal minus 1 and the C equal 3. They left off that A was equal to 1. Okay, here's the second part. So I'll do it on this screen. Okay, the B part is the integral from of 18 over x plus 3 times x squared minus 9 dx. So do we proceed like before? A over x plus 3, bx plus c over x squared minus 9. Why not? That's factorable. You only do that bx plus c over a quadratic if it's an irreducible quadratic. That's not irreducible, so we factor it. So the first thing we do is factor. And how does that factor? Well, the x plus 3 is x plus 3. How does x minus 9 factor? X plus 3 times x minus 3. Well, here we have the other problem, isn't it? We have a multiple factor, okay? So you could write that as, and I will, as 18 over x plus 3 squared times x minus 3. And you remember what the rule for doing that was. A over x, which you say? Minus 3 will be fine. Plus b over x plus 3 plus c over x plus 3 squared. Yes, okay? The only time you put an x in the numerator is if you have an irreducible quadratic in the denominator. Here we don't. It's just a binomial to a power, so you just do that. Okay, what's the next step? By your denominators. Okay, So this denominator go out completely. This one, the x minus 3 will go out, and it'll leave you an x plus 3 squared. Okay, this is ugly, but we'll clean it up later. Here, one of the x plus 3's go out, leaving you an x plus 3 times the x minus 3. And on the last one, the x plus 3 squared goes out, leaving you only an x minus 3. So, what is your resultant line? 18 is equal to a times x plus 3 squared plus b times plus 3 times x minus 3 plus c times x minus 3. What's next? Second? What do you want to plug in? Second?
3.
Okay, let x equal 3. Left-hand side stays 18. Right-hand side becomes, and by the way, oh no, we're already past that, okay. If you do a 3 here, what do you get?
36A.
Second?
36A. 36A.
Yeah, 36A, okay. All right. And 0, 0. All right, which implies that A is equal to 1/2. Next, -3. Okay. And that will give us 18 is equal to minus 6c. Is that what you said? Okay, my hearing's so bad. And that implies negative what?
3.
Yeah, 3. Okay. All right. Haven't gotten the b yet, though, have we? What you want to try for that? Okay, let's try x equals 0 with the others that we've already found. So that'll give you 18 is equal to, your a was 1/2, and what do you have with x equals 0 then? 9/2. Got it? Plus, we don't know the b, so the b is going to be there. And what do we get after that? Minus 9. So we're going to make that a minus 9b. Oops. Pen's not picking up. Okay. Minus 9b plus, minus, c is 3. Well, okay, c was a minus 3, and then another, so that's going to wind up being a plus 9, right? Okay. Doesn't look very pretty, does it? Okay. Let's multiply everything by 2 to get rid of that fraction, okay? But before we do that, let's add 9, subtract 9 from both sides. So this will make this a 9. Okay. Now let's multiply by 2. Well, let's divide by 9. Okay. And multiply by 2. Okay. That'll be 2 is equal to 1 minus 2b. Right? Done an awful lot of steps there. So this will be 1 is equal to minus 2b, meaning b is equal to negative 1/2. Now that's what I got. Let's make sure that I haven't made a dumb error somewhere here. B is equal to negative 1/2. Good deal. Okay. All right, we got our A, B, and our C. What it now becomes our integral. One half. You know, do we need to write the integrals again? Yeah, we might. Let's go on and do it. Dx over x minus 3, right? Minus 1/2 the integral of dx over x plus 3 minus 3 times the integral of dx over x plus 3 squared. Believe I got it right. Okay? So what does that come up being? Natural log of x minus 3, absolute value, minus 1/2 natural log of the absolute value, x plus 3, minus, well, I think that's going to wind up being a plus, isn't it? 3. Say that one more time. Yeah, plus 3 over x plus 3. I believe is how that works, right? And then you got a plus c. All right. Let's see how they did it. 1/2 x absolute value x minus 1/2 log absolute value x minus 3 minus 1/2 log absolute value x plus 3 plus 3 times x plus 3 to the minus 1, which is the same as over x plus 3 plus c. Got it. Okay. Now, I think the next few slides have some of those steps in them. Let's just see. No, they don't. They didn't do any of those. So this is the next example. Any questions on that? Oh, we still had it up. Make sense? All right. What if we have repeated quadratic factors? They were wanting to do that all along, but so far they haven't given us an example. So here's the next example. The integral of 4 minus x divided by x times x squared plus 2 squared dx. What we gonna do first? I'd say first thing to do, note that is an irreducible quadratic. X plus 2 squared can't be reduced. Okay? So what are we going to do with it? Anything? First step, a over x, first factor. That's the easy one. Okay? Plus how about, yeah. Now, do you want to use different letters or subscripts? Huh? Different letter. Okay, bx plus c over x squared plus 2 plus dx, is that what you wanted? plus e, I like that better because I'll lose subscripts, over squared. Got it. Next, a lot of those denominators. So that'll wipe out that denominator altogether. It'll wipe out that one, leaving you an x squared plus 2 squared. Okay. The next one is going to have an x, also going to have 1 x squared plus 2. Right? Wipe out that one. The last one, the x squared plus 2 squared, goes, leaving you only an x. So let's write down what our result is there. 4 minus x is equal to a times x squared plus 2 squared plus, okay, I don't know where I want to put it. Let's put it in the other one. Bx plus c, and let's multiply the x in there. Not yet. We'll do it later if we need to. X times x squared plus 2. Okay. And here we'll have plus dx plus e times x. We're going to have to multiply it sometime, but let's not do it yet. What's the next step? And what do you want to plug in? X equals 0. I like it. Okay? And this will have 4, is that what you said? Yep. Is equal to 4a. And that's all it wrote. Which implies a is equal to 1. You picked the easy one, didn't you? Okay. Is there anything else? Any guesses? Nothing easy like that. You had that. Hope you enjoyed it. Okay. So why not, with a equal 1, pick another x? Guess what? Can't use 0, so why not 1? I like 1 fine. So let's let x equal 1. Okay. Okay. So what would you have here? 3 is equal to, and we got a equal 1. So that will be yeah, 9 plus, and there's nothing we can do with the bx plus c yet. But what's the rest of it? Three. Okay. I think what I'm going to do, because I sort of like to put them in front, I'm going to put my plus 3 here. Okay. That's a little better. Okay. Plus. Okay, wait. I left the x in there, which you let me do, and I shouldn't have. That's just a 1, right? Okay. Don't let me do that. Okay. And this will be then dx plus e. Okay. What's that? I was planning not to put it in there, and there I put it in anyway. Okay. D plus e. Okay. Here's what I'm going to do with this. I'm going to write it this way. if it's okay with you. I don't want to do anything you have objections to. 3b plus 3c plus d plus e is equal to negative 6. Okay with that? Guess what we got to do next? Second? I wouldn't. I don't like fractions that much. But if you like fractions, go for it, okay? There's nothing you can do to solve for one of those yet. So guess what we got to do? Plug in something else. Now, this is where this method may take you a little extra time, because guess what you're going to wind up with? Equation 4 unknown, which you're probably going to have to do with a matrix. Have y'all done much matrix algebra? And then I'll have to teach you matrix algebra now. Okay, it's not bad. It's really pretty good so far. Not sure what I'm about to suggest we do is going to be a lot better, but it might be. Okay? Let's do that other method that we have. Okay? It's called the undetermined coefficients. I have a sneaking suspicion it might work out a little better. Y'all have got that written down, so if we need to come back to it, we can do it without recreating it. Let's do the undetermined coefficients and see if that might be a little easier on this case. Okay? We've got our a equal 1. So what we've got now is 4 minus x is equal to x squared plus 2 squared, which I think I'm going to have to go on and multiply. So let's save a step and do that. Okay? A is 1, so fine, it's out of the way. So let's multiply that. Square that binomial. X to the 4th plus 4x squared plus 4. Everybody see that? You know the shorthand for doing that, shortcut for doing it? Square the first, twice the product, square the last. That's what we get. Okay? Plus, I'm not sure this is going to help any, but let's try it. Oh, do I really want to do this? Okay. First thing I'm going to do, and this is what I was tempted to do before, and I didn't, but now I'm going to do it. I'm going to change this to x cubed plus, can anyone read my writing there? That's a 2. 2x, right? X cubed plus 2x. Wasn't that what it was? X times x squared, yeah. Alright. Okay. So let's multiply those together. That gives you bx to the 4th. Let's do this one next. Cx cubed. Now let's do this one. 2b x squared. And then let's do the last one. 2cx. Okay? And then we've got a plus dx squared plus ex. Buy all that? Okay. Now, what we're going to do now is match up terms on this side with terms on that side. All right? Okay. And frankly, the only constant we have here is 4 and 4. So we can subtract those away. Okay. Gone. Okay. Now let's match the rest of them. How many x fourth terms you see on the left? None. So that means that b, 1 plus b is equal to 0. Do you buy that? Because all your x fourth terms here are, I hope I got them all, is x to the fourth plus bx to the fourth. And that adds to 0 because there aren't any x to the fourth there. So that means that b is -1. Okay? So we've taken care of the x to the fourth terms. Okay. Guess what you see about the x cubed terms? There aren't any on the left, so it better be a 0 coefficient there. And how about on the right? 3. So basically it's saying c is equal to 0. You see that? Because there's no x. Your only x cubed term here is 0 x cubed. So that means c is equal to 0. Okay, so we're taking care of the cubic terms. Okay, let's take a look at these quadratic terms. What do we have on the left? None. How about on the right? 4 plus 2b, but b is -1, so that'd be -2, right? Plus d. Buy that? Okay. Now that looks like to me that would imply that d is equal to -2. Is that what you see too? Also? Whatever. Okay. Now let's look at the linear terms. On the left we have -1 is equal to, oh, we're taking care of the quadratics, I hope. Yeah. Okay. And c is 0, so that one's gone. So this is equal to e, isn't it? So e is equal to -1. I think that might be a little easier than a 4x4 system of equations, right? Okay. So what do we have? A drunken sailor, okay. You have the integral of, your a was 1, so it's dx over x, right? I think it's going to wind up being a minus integral of, b was a -1, so that's just going to be a x dx, right, over x squared plus 2. Goodness, my writing stinks, okay? X squared plus 2, right? Let's see, is it going to be a plus? No, I think it's going to be a minus also. Integral of x plus 1 over x squared plus 2 squared dx. Okay. It's getting crowded, so I'm going to erase some stuff, even though it used to be important. We have it all down pat now, I hope. Okay. I think that's what that becomes, doesn't it? I hope so too. Okay. All right. I think I can do that first one. What is it? Natural log of x. Absolute value of x, by the way. Okay. How about that next one? Just gonna leave it 1/2. I think I hear the gears grinding in there, don't I? Okay, yeah. Good start. Natural log of x squared plus 2. And that doesn't have to be in absolute values, because that's always positive. Okay? Now this next one. Ooh, grind some more. I think we got to split it, don't we? Okay. So let's get rid of some stuff here so I can write this better. I hope I've got everything I need done already. Okay. So this is going to be a minus the integral of 2x dx over x squared plus 2 squared, right? Minus dx over the integral of tx over x squared plus 2 squared. I'm not liking that last one at all, frankly. First one's not too bad. What do you think it is? Okay. Get my pen back in hand. I'm going to have to erase a bit more, I think. You know, I should have been checking and make sure we got the same coefficients they did. Were y'all doing that for me? You weren't? Okay, let's see what we got. I'm not showing it here, but A better be 1. A is equal 1, I see that. B is equal to -1, C is equal to 0, D is equal to -2, and E is equal to -1. Okay, okay. Feel a lot better now. Okay, so this again was log absolute value x minus 1/2 natural log of x squared plus 2. Now that one. Plus 2 over what? 2 over x squared plus 2? Is that what? Yeah, over x squared plus 2. Okay, is that all you have on that one? I have to stop and think a minute. If you do a substitution, then that numerator is your 2x dx. Okay, and that would be u to the minus 2, which is minus u to the minus 1, right? So I don't think there's a 2 in there, is there? Okay, all right. That's what was throwing me. So I believe that's a plus 1 there. Am I convincing you or screwing you up? Yeah. Okay. Sometimes it's going to bite the bullet and write it down, but I think that's right. Now that last one. Oh my word. Now that's not exactly the form we had before, because you got a square down there. You know where I'd go? A table. Okay? Well, let's see if we can find an integration table that will be helpful. Certainly find integration tables, I think. Finding them that will be helpful is another matter. Here we go. Too many pages stuck together. I'm not seeing anything in the back that's really particularly helpful. A big boo hiss. Okay? Now, if y'all have any, huh?
Is that not just
Which one?
1 over x plus 2?
1 over.
X squared plus 2.
Okay, say that again. Is that your a substitution you're going to do, or?
No, sir, I was just looking at it in parentheses.
Right.
It's a square.
Yeah, it's x squared plus 2 squared. It's the same denominator as here, but it was the minus 1 in front. Okay. Now I'm beginning to think we ought to go back to this and try to work it together. Let's try that. Okay. Let's go to this and try a substitution. Let u equal x squared plus 2. Then du is equal to 2x dx. Do you buy that? Okay. It's not going to get any better.
What if you broke that second down into 1 over x squared plus 2?
Okay, you're just going to do this one now? Yeah, that's where I was going to go next. And what were you going to say?
So break it back.
How?
Do 1 over x squared plus 2 plus 1 over x squared plus 2. Is that the same thing?
Oh, okay. You mean do another integration partial fraction with it? That might be it, now that I think about it. But it seems like we're almost going to be running in circles then.
What's the next slide?
What's that?
The next slide.
Yeah, let's turn the page in the book and see what they're going to do. All right, yeah. They say, what they say to use, and is one thing I was thinking, but I didn't think it was going to do, is do a trig substitution, and that's your typical tangent. Let x equal a tangent, which will be the square root of 2 tangent theta. Then dx is equal to square root of 2 secant squared theta, right? D theta. Okay? Now what do we have? You have minus the integral, and let's pull the square root of 2 out, secant squared theta d theta over okay, that would be, let's just do this, x squared is equal to 2 tangent theta, 2 tangent squared theta, right? Okay. Add 2 to that, and you get 2 times tangent squared theta plus 1, which is secant squared theta. Okay. So that's your x. No, that's your x squared plus 2. And then you're going to square that, and you get 4 secant fourth theta. Right? Okay. So your numerator is secant squared theta. Your denominator is 4 secant fourth theta. Right? That leaves you a secant squared in the denominator. Yeah, which is minus square root of 2 over 4 times the integral of cosine squared theta d theta. And that is in the back, cosine squared u du is your 1/2 u Alright, so you have a minus the square root of 2 over 4, and that integral of cosine squared is a 1/2 theta plus 1/4. They do sine of 2 theta. I like that other form better, which is 2 sine theta cosine theta. So that would be 1/2 sine theta cosine theta. Okay. So that's what that is. Alright, now how you evaluate what is what. We know what theta is, and that's the inverse tangent of x over root 2. So yuck, I don't have any room. Okay. And I've just, okay, I'm going to erase my constants. We know those are right. Okay. So this last one is a minus times a minus is a plus. No, wait. I think I carried that minus with me, so let's not do that. If I'm off by a sign, it's because I've gotten lost how many signs I've got. Okay. The square root of 2 over 4 times 1/2 the inverse tangent of x over root 2. Okay, that's that part. I'm going to keep the plus here now. Now, it's time to do our little triangles. Okay, so I'm going to erase some room here to do our little triangles. From our first assumption on this one. Let x equal square root of 2 times the tangent of theta. I just had it, set it, but okay. If this is theta, tangent theta is x over root 2. Okay, which makes this side over here the square root of x squared plus 2. Okay, so sine of that would be x over, okay, so this will be plus 1/2 x over the square root of x squared plus 2 times cosine of that would be the square root of 2 over the square root of x squared plus 2. Now this is all that last thing here. These two multiply and lose the radical. So, and here we have a square root of x, square root of 2 times x over 2. Let's just pull out. So this will be a minus square root of 2 over 8 inverse tangent of x over root 2 minus x root 2 over x squared plus 2. Okay. Now, if I put the parentheses there, it does like that. So let's see how far off we are. Whoops. Oh man, did I lose my... Yes, I did. Someone tell me what page I'm on. Methods of partial fraction. Who wanted to do this one anyway? Okay. Here it was. Okay. So we have log x, got that one, minus 1/2 log x squared plus 2, got that one. Oh, flip the page. Now the trouble is I have a plus and they have a minus. I've already... No, they have a minus. So I don't know. I guess there it is. I'm not sure. I'm not going back and finding it. They have that being a minus there, so I'm okay with that if they are. Okay. And then this last integral. Okay, here's the final answer. Log absolute value x minus 1/2 log x squared plus 2 Okay, they combine some terms and all sorts of things. Because you see, this term has a 1 over x squared plus 2, and down here we have another one with a x root 2 over x squared plus 2. But that had a thing in front of it. So if you, I'm going to have to do this. I was hoping not to, but I'm going to have to. This would be a minus 1/8, square root of 2 over 8 times the inverse tangent of x over root 2. Okay. And then when you do that one, that's going to be a minus, and the root 2 times root 2 is 4, so that's going to be 1/4 x over x squared plus 2. Okay. That's when you break those up. I think that's a minus on there that didn't show up. Okay. So, when you combine this term with that term, this kind of drives me nuts. At the top they had it being a minus, and then at the bottom they have it being a plus. So I think we were right and they were wrong, but it's a plus 1, not a minus. I think that's a plus 1. So plus 1 minus 1/4 x all over x squared plus 2. That's combining those two terms. So I had it right before. And the last one is 1, I have a root 2 over 8. They write it as 1 over 4 root 2, which usually you try to rationalize denominators. They put the rational in the denominator. Inverse tangent of x over square root of 2 plus c. Goodness gracious, what a problem. So yeah, trig substitution was where to go on that. Conceptual insight. Examples illustrate a general fact. Now this is worth noting. The integral of a rational function is always expressed as a sum of either other rational functions, okay? Now that may be if you have an improper rational function to begin with, so that's going to give you some rational functions in front. This example here had a rational function in it, okay? So rational functions, arctangent, this one had an arctangent in it, of linear or quadratic polynomials. This happened to be linear in this one, but it could have quadratics, and logarithms of either linear or quadratic polynomials. Other types of functions, such as exponentials, trig functions, do not appear when you're using partial fractions. When you can use it and you use it, these are going to be other rational expressions, logs of either linear or quadratics, and inverse tangents of either linear or quadratics. Done. Now the next little part says using a computer algebra system. So if I don't have one, if you have one that you have access to, go for it. Use it. All right, the summary goes over what we just did, so you can certainly go back over that. Do you find the preliminary questions helpful? Okay, let's see what else they got on the slides here. That's what we already did, I think. Yeah. You had done that substitution basically in your head, and you got down to this. And there's where they put the minus sign, and well, not going to worry about it now. There's your little triangles, which are always really good, especially when you're back substituting and you have sines and cosines where you had tangents before. That's helpful. Well, no, they don't have any, so let's do them here. Okay, suppose that the integral of f of x dx is equal to natural log of x plus the square root of x plus 1 plus c. Can f be a rational function? Explain. Now, the very first preliminary question here is based on the very last thing we did. Okay? Do you think that's going to be a rational function? Can f of x be a rational function? If you lose the square root there, it is. If that's just x plus 1, that's a rational function. Square root of x plus 1 is not a rational function. So therefore, no, that form is not allowed. Okay, or that's my reading of it. Let's see what their reading of it is. I hope I'm not telling you something wrong. 7.5 preliminary question. No, f cannot be a rational function because the integral rational function cannot contain a term with a non-integral exponent such as square root. That's exactly what we said. Okay, number 2. Which of the following are proper rational functions? See, it seems like to me this should have been number 1. X over x minus 3, 4 over 9 minus x. X squared plus 12 over x plus 2 times x plus 1 times x minus 3 and 4x cubed minus 7x over x minus 3 2x plus 5 9 minus x. Okay? Which of those four are proper rational functions? Any of them? None of them? All of them? What? First one what? Is not. You're right. Same degree. Okay? Yes. The B one is. And you say D is too? C? B is? C you say is? Yeah. Good. How about D? No, because it's a cubic on top and a cubic on bottom. Okay? So it's only B and C. It better be B and C. They don't have the evens in. Okay, so it is B and C. Okay. I just said so. All right, number 3. Which of the following quadratic polynomials are irreducible? Okay. X squared plus 5. X squared minus 5. Oops. X squared plus 4x plus 6. And x squared plus 4x plus 2. Now, time out. When we say irreducible, that doesn't mean we can factor them with integers. So we can factor them with real numbers, including irrationals. Okay? Any ideas? Which of those are, which was the question? Which of the following quadratic polynomials are irreducible? It's kind of a negative there. Or not reducible would be another way of saying it. Say again? The first one you're saying is irreducible. Is that what you're saying? Which is following? Yeah, I agree. Okay. Is that the only one? Second one, what?
It's just as bad. Can you reduce the second one?
Yeah, you can with the square root of 5. Plus minus the square root of 5. Yeah, that is reducible. In the real numbers, not reducible with integers, but with real numbers. Okay? Next one. You want me to give you a hint? The hint will be your good old, you remember what was called the discriminant? The quadratic formula? When you had b squared minus 4ac and the radical. That determined whether that was going to be. If that came out being positive, then you're fine. If it came out being negative, you're not fine. Let's do this one just for fun. B squared, 0, minus 4ac, that's going to be negative. Not reducible. This one, b squared, 0, minus 4 times a, that's positive. B squared, 16, minus 4 times 24, negative. 16 minus 8. That's the easy way to do this. So, the ones that are irreducible, A and C. Didn't we say? Yeah, A and C. Better be A and C, or else I gave you a shortcut that doesn't work. Oh, they say them all. Square is already completed. They say, and I'm sorry, they say to check, complete the square if necessary. Okay? I find using the discriminant far easier. But they say the square is already completed, irreducible. Whatever that means, it's irreducible. We said that. B, the square is already completed. It factors plus or minus square root of 5. Okay, we knew that. So it's reducible. Next, irreducible. Next, you can reduce it. They take it by completing the square. Please. Okay. Way too much work for me. Okay. Do the discriminant. Far easier, I think. And so far it hasn't got me down. Messed me up. Let's look at 4. Let P over Q be a proper rational function with where Q of X factors as a product of distinct linear factors X minus A to the I. Okay? So P over Q proper. So we got the first thing taken care of. Okay? Q factors as distinct product of X minus A to the I. Well, those are different A's. Then the integral of P of X over Q of X dx. And it says choose the correct answer. A. Is the sum of logarithmic terms A sub I times, okay. And those terms would be A sub I, the ln, they really should put this in absolute value, X minus A sub I. Okay? For some constants AI. Okay? Or B, may contain a term involving an arctangent. They like arctangent, I like inverse tangent. Which of those you think is true? Or both, or neither? They say choose the correct answer, suggesting only one of them is. Huh? A, definitely. If that has distinct factors like this, guarantee they're going to be sum of log terms. Okay? And by the way, one of the key words there is distinct linear factors. In other words, none of these are repeated. Okay. That's one key term. Proper, of course, was another. And then when you do that, that means your sums are all dx over this, dx over that, and with just constants in front. So yeah, that's definitely it. Only time you get the inverse tangent is if one of those is an irreducible quadratic. That's a linear. That was the other key term. I knew there was another key term in there. Okay, and I don't think those answers are in the back. That answer's in the back. Let me just check. Yeah, they only had 1 and 3. Homework exercises here. I would definitely do 1. Okay. You're matching A through D with Roman numerals I through 4, so that shouldn't be too bad to do. But you can do 3 or not. I'll let you do that. Pretty easy. Either 5 or 7 or both. Any of the odds, here's the passel of them, maybe a passel and a half. Any of the odds 9 through 45. I mean, they got a bunch of them there. So do some of every type, or several of the types. Then do either 47 or 49 or both. And then you could try any of the odds 51 through 57. Okay? 51 talks about rationalizing substitution, which is sort of an interesting thing. They give you a pretty good hint there. And then, yeah, I was going to see if there's any more, though, that might be a potential paper topic. I don't see any. Okay, I think that's it for 7.5. Finally, that was much longer than I was anticipating. Let's at least look at what 7.6 is doing. It's kind of tying up all the loose ends, okay? Even if they're not too loose. Well, it's going to take a while to open. What have we got? 5 minutes? Okay. 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 Wow. No slide help here for pages, okay? In fact, I don't even think there's any. That's the next section. So either the old edition didn't have the strategies, or else it's a different section. So let me go and check. What a pain. To see if it's in a different. I thought they had this in the previous. That, I think, is our 7.8. Yeah. So let me try 7. There's 7.8. I think we have a 7.9. Oh, yes, we do. Yeah, sorry. They don't have a 7.6. So that's where we'll start next time. Well, they don't have the strategies for integration. I guess it was back in chapter 5 I was thinking that they had something like this. First thing to do when you are doing this, trying to do these integrals, do any algebraic simplification possible. Okay? What I'm going to do is, this may take longer than it's worth, because now we only have 3 minutes left. Yeah, okay, that didn't take too long. Okay. I think I'm going to need my pen color. Okay. In general, there's no hard and fast rules for evaluating a given integral. Okay? There are some various heuristics, whatever they are, to help us determine which techniques to apply. So here's the deal. First, do any simplifications possible. Here's an example. The integral of x cubed minus 1 over x minus 1 dx. Okay? Any chance of integrating that? Doesn't look promising, does it? Until you remember, I'm sure you remember, how to factor a difference of two perfect cubes. Don't you? No. Okay. Here's the rule for doing that. The first term in the factor, there's only two factors. The first term is the cube root of the first, same sign, cube root of the second. Okay? The next term forget about what you start with. Let's just look at that first term. Square the first, x squared, opposite the product of the two, plus x, square the last. Okay? Now, if you don't believe me, multiply it out and see. X times x squared, x cubed, minus x squared, plus x squared, 0, minus x, plus x, 0, minus 1. Sure enough, that works. Don't ever try to factor that. It will never, ever, ever be factorable. That's an irreducible quadratic. Well, in integers anyway. Okay. Approach it with the radicals. So let's see. Minus b squared minus 4. No, it's not going to work. Okay. So guess what we can do? And then I think we can integrate, can't we? Anyone want to tell me what the answer is? X cubed over 3 plus x squared over 2 plus x. Not, plus c, okay. Okay. Not quite. Semicolon, x cannot equal 1. Because guess what? If it can't equal 1 there, it can't equal 1 in your answer. Okay. So to be strictly correct, you need that in there too. Any other x will do, but not x equal 1. If you were to graph that or something like that, you'd have to have a hole in the function of x equal 1. Okay. And we've run out of time. We'll start next time. That was worth it, wasn't it? We'll start next time at the B. Oh, and the book didn't put that little thing in there about x can't equal 1. I threw it in. But no extra charge. Okay. So, okay.